This is a video for pre-calculus for chapter 4, section 3, and it's about reflecting graphs and whether or not a particular function has symmetry. And if a particular function has a certain kind of symmetry, it can be classified as an even function or an odd function. And we talked about that before when we studied even degreed functions and the sum and difference of the sum and product of their roots compared to odd degreed functions and the sum and product of their roots. So the different types of symmetry that we're going to talk about, we'll start with symmetry in the x-axis. And so if something has symmetry in the x-axis, or if we want to reflect something about the x-axis, then we say that the ordered pair xy gets mapped into the ordered pair x minus y. And so if we had a function like y equals x squared plus 2x minus 3, and we wanted to check for symmetry in the x-axis, then what we would do is we would plug in x for x, and we would plug in the opposite of y for y. And if we get the same statement, then it has symmetry in the x-axis. And what we mean by that graphically is this particular parabola, the vertex is going to be, I think it's going to be down here somewhere, just estimating, and it's going to open up like this. And to have symmetry in the x-axis means that if I flip it around that, the x-axis, it's going to land on itself, and obviously this parabola will not. But this parabola would. Let's get that over a little bit. This parabola would land on itself if I flipped it over the x-axis. So the parabola I'm looking at, and I'm just going to throw that on my graphing calculator to make sure, x squared plus 2x minus 3 it does look similar to what I was saying, but if I were to spin this on that x-axis and the vertex was up here instead of down here, then my parabola would open this way, okay? And so as far as this particular function having symmetry in the x-axis, it does not. But I can reflect it about the x-axis. And to reflect it about the x-axis, what I do is I take the ordered pairs. Like I said, the vertex looks to be at -1, -4. So what it does for the reflected graph is exactly what it says to do up here. xy gets mapped into x minus y. So the reflected graph, the vertex would be at -1, 4. And this graph, the y-intercept is -3. For this graph, the y-intercept would be 3. The x value stays the same, and I change the y value. And then I could draw the reflected graph. You know, if this is that graph, then the reflected graph could be like this, okay, where it's going down through. So to check for symmetry in the x-axis, I plug in the opposite of y for y, and I plug in x for x, and if I get the same equation, then it has symmetry in the x-axis. If I don't, then obviously it doesn't. And in this particular one, if I change y and leave x alone, that is not an equivalent statement, because I would solve this for y, get minus x squared minus 2x plus 3. Those aren't the same parabola. Okay? So there is no symmetry in the x-axis for this particular function. Okay. So then we can check for symmetry in the y-axis. And you can imagine then xy gets mapped into opposite of x, y. And because graphically what we're doing is we're throwing that thing over the y-axis. So any parabola whose vertex is on the y-axis is going to have symmetry in the y-axis. Okay, so if I spun this thing on the y-axis going this way, okay, then notice that this x coordinate, where it's positive here, will become negative when I spin it over here. Okay, so again, the parabola that I used up above, y equals x squared plus 2x minus 3, that parabola does not have symmetry in the y-axis, because again, you know, that vertex is here, the y-intercept is here, and it goes something like this. And you know, if I leave y alone and I change x, would actually be minus x squared plus 2 times minus x minus 3, I get x squared minus 2x minus 3. That's close. It's close, but it's not the same. So therefore, we say, you know, this parabola does not have symmetry in the x-axis, in the y-axis, sorry. But no symmetry in the y-axis, but I can reflect it about the y-axis. And the way I do that, again, is I take my original function. So here's my original function, and here's my reflected function. And I do exactly what it says. Like we have the vertex is at -1, -4. The vertex for my reflected function is going to be at 1, -4. And the y-intercept is at 0, -3. And actually reflecting it over the y-axis, this is going to stay the same, 0, -3. And then I could find other points. For example, the -3, 0, and 1, 0 are the x-intercepts. So on the reflected graph, those points are going to become 3, 0 and -1, 0. Okay, if I reflect it over the y-axis. So I could draw, you know, I could draw the original function, and I could draw its reflection over the y-axis. I can also then, like we did before, we checked for symmetry in the y-axis, and there was no symmetry in the y-axis. Okay. The next two are a little bit more interesting than just reflecting it over the x-axis or reflecting it over the y-axis. The next two is, first we'll look at symmetry in the line y equals x. And what that means is that in terms of, you know, what xy, what that means is that xy gets mapped into yx. And this one is highly important because if we have symmetry in the line y equals x, or if we reflect something over the line y equals x, the reflection we get is actually the inverse of the original function. Okay. So again, we can go through all those things. Here's the line y equals x, and to have symmetry there, like I can take my parabola that I've been working with down here, okay, and if I flip it over the line y equals x, then this vertex, which is at -1, -4, becomes a vertex at -4, -1 over here. And it's going to open this way now. Okay, so its reflection will be something like that. And as I said, the reflection, when I reflect over the line y equals x, is actually the inverse of that function. And in section 5 of this chapter, that's what our focus will be, is whether or not a function has an inverse, because in order to have an inverse, the function has to be 1-to-1. And then if it has an inverse, finding the rule or the equation that would map that inverse, and then also proving that, using the composite function to prove that yes, indeed, we do have an inverse. Okay. So if I had my equation y equals x squared plus 2x minus 3, the way I check for symmetry is I interchange x and y. And if I do that, I get x equals y squared plus 2y minus 3. And obviously, those are not the same equations. Okay? This is a parabola that opens up. This will be a parabola that opens to the right. Okay? So, no, there is no symmetry in the line y equals x for that function. But just like the other equations, I can take my original set of ordered pairs, -1, -4, and for the reflection, for the reflected graph, that ordered pair becomes -4, -1. Or we had 0, -3 as a point on that graph. In the reflected graph, that point would be -3, 0. And so on, and the list goes on. One of the x-intercepts was 1, 0. Over here, that'll be 0, 1. Okay, and we can graph that, graph this parabola, and that will be the reflected graph. And that's kind of what I graphed here. Even though the parabola isn't 1-to-1, it can still have an inverse because I'll restrict the domain. And so, this becomes the inverse of the right side of the parabola, and this becomes the inverse of the left side of the parabola. And we'll talk more about that when we get to inverses. But reflecting over the line y equals x is a bit more interesting than just reflecting it, over the x-axis or over the y-axis. And then that brings us to our fourth and final reflection, and that's reflection or checking for symmetry in the origin. And symmetry in the origin is kind of cool, because what it does is basically it reflects it over the x-axis, then it reflects it over the y-axis. Okay, it's double that. So in order to check for that, xy, I don't know what I was doing there, xy gets mapped into minus x minus y. Because remember, when xy gets mapped into x negative y, that's a reflection over the x-axis. And when xy gets mapped into negative x positive y, that's a reflection in the y-axis. So a reflection about the origin is doing both those things. I'm reflecting it over the x, and then I'm reflecting it over the y-axis. And what I get is, so if we use my same example, y equals x squared plus 2x minus 3, and I check for symmetry in the origin. That means I'm plugging in minus y for y and minus x for x. And so I get minus y equals x squared minus 2x minus 3. And then if I get rid of this negative on the y, I get minus x squared plus 2x plus 3. And obviously that and that are not the same. So as far as this function having symmetry in the origin, it does not. But I can reflect it about the origin. And so again, I can take those ordered pairs, -1, -4, and for the reflected graph, -1, -4 becomes 1, 4. And then 0, -3 was the y-intercept, becomes 0, 3 for the reflected graph. And then 1, 0 was one of the x-intercepts, becomes -1, 0. And the other intercept was -3, 0. And so -3, 0 becomes 3, 0, and so on. And so I can graph the original function, I can graph its reflection about the origin, and just by changing those ordered pairs, okay? And so, as far as homework goes, we will be concentrating on, like in the first part, we have, they give you the equation of a line, like y equals 2x minus 3. And they're saying sketch the graph of this, and then sketch the graph of the reflection over the line y equals x. And then give the equation of the reflected graph. Okay, so here's how I do that. First of all, I graph it. And I don't need to list ordered pairs to graph this. Okay, so the y-intercept is -3, the slope is +1, so I'm going to rise 2 and run 1 and draw in that line. Okay, but it is helpful. So I graphed 0, -3. I graphed 1, -1. 2, 1 would also be on that graph. It helps to have the ordered pairs when I want to look at the reflected graph. Okay, so the reflected graph is going to have, and I'm reflecting over the line y equals x. So that means xy gets mapped into yx. Okay, so my points become -3, 0, -1, 1, and 1, 2. So -3, 0 is over here, -1, 1 is here, and 1, 2 is here. So there is the graph of the reflected graph. Okay, and here is your line y equals x. So this is reflected over that, okay, over that line y equals x. And that's the graph that we get. We could label this f of x. And for now, we could label this g of x. Okay. What they want me to do now is they want me to find the equation for that graph. Well, it's linear. It wouldn't be hard to figure out, right? But there's an algebraic way to do that. My original function is f of x equals 2x minus 3, or y equals 2x minus 3. the algebraic way to figure out the equation of the reflection is to do exactly what it tells me to do right here. To take xy and change the x to a y, change the y to an x, and solve it for y. So I do that. I take and I make the y x, and I make the x y, and then I want to solve that for y. And so I get x plus 3 equals 2y, divide everything by 2, and I get 1/2 x plus 3/2 equals y. And then, as I said, if we're using function notation, we can change that to g of x equals 1/2 x plus 3/2. Okay, and we just did that reflection. Okay, and then you'll have some absolute value graphs to do. And if I can make something up here, I don't know, y equals the absolute value of x plus 3. Okay, so I'm supposed to graph that. So I am going to make a table of ordered pairs. If I plug in -2, I get 5. If I plug in -1, I get 4. If I plug in 0, I get 3. If I plug in 1, I get 4. If I plug in 2, I get 5. So let's 0, 3. Here, and then 1, 4, -1, 4, 2, 5, -2, 5. So, so graph of absolute value is a V, all right? Not a curve at the bottom like a parabola. It's a point at the bottom, like a V. And if you remember, this would take the parent function, and this would move that parent function up 3. And so, this graph makes total sense about where I am, okay? And I want to reflect that over this line, y equals x, okay? So to do that, the ordered pairs of the reflected graph will be 5, -2, 4, -1, 3, 0, 4, 1, and 5, 2. And some people can just visualize that reflection and draw it in. I'm not one of those people. I got to have the ordered pairs. So 5, -2 is here. 4, -1, 3, 0, 4, 1, and 5, 2. So I don't know how that point got off, but it's off. There's my reflected graph, okay? And then we're supposed to write the equation of that graph. And what we will do for that is what we did, for, there's our original function. We interchange x and y, and we get this. And we're not gonna solve that for y. The only time we're gonna solve for y is if it's a linear equation or a quadratic equation, or if it's like a cube, y equals x cubed. Like if we interchange x and y, we can certainly solve that for y. But we're not going to solve this for y. We're going to leave it just like that. Okay. And when we get to inverses, because that's basically what we're finding here, is we're finding the inverse. This is the function. This would be the function's inverse, because when I get reflected over the line y equals x, that's what I'm getting, is its inverse. When we get to those, we'll be restricted to, linear equations and quadratic equations is what we'll focus on for those. Because I really don't think we care about the inverse of an absolute value problem. But it's good to have an understanding of what it means. Okay. So there are some more problems, like where they give you a parabola in what I call graphing form. So number 21A is y equals the quantity x minus 3 squared plus 5. And we're supposed to graph that. And then we're also supposed to graph on the same set of axes the x equals y minus 3 squared plus 5. Okay. So basically, what they've given me here is they've given me the function and its inverse. Okay, we can tell that because all they did to get this new equation was interchange the x and the y. Okay, so the vertex here is 3, 5, and the vertex here is, if I move this 5 over here, it would be 5, negative 3. No, it'd just be 5, 3. Sorry. So 2, 3, 4, 5. 2, 4, 5. 4, 5. Okay. So 3, 5 is the vertex of the original one. If I plug in 2 up here, I get 1 plus 5, I get 6. 2, 6 is a point, and that means that 4, 6 is a point. Okay. There's a parabola, so it's curved at that bottom, right? Okay. This one's vertex is at 5, 2, 3, 4, 5, 3, 3. And if I plug at 3, so if I plug in 2 for y, okay, I'm plugging in 2 for y, I get 2 minus 3 is negative 1, squared is 1, plus 5, I get the 6 for x. So 6, 2 would be a point. Remember up here the point was 2, 6. And then the other point, this point was at 4, 6, right? So if I plug in 4 for y, I get 1. And but plug in 4, I get 1, and 1 squared is 1, plus 5 is 6. So I also have a point at 6, 4, right in here. And there's that graph. And if we look at it, looks to me like it's a reflection over the line y equals x. they want you to show the axis of symmetry and the equation of the axis of symmetry. So this axis of symmetry would be x equals 3. This axis of symmetry, this axis of symmetry would be y equals 3. The parabola that opens sideways, so the axis of symmetry for this one is going to be a horizontal line. I think that's all they wanted you to do for that. So then the last thing is, what defines an even function versus an odd function. And if xy gets mapped into minus xy, then we have an even function. And what does this mean? This means that I have symmetry in the line, or not in the line, we have symmetry in the y-axis. So something that has symmetry in the y-axis would be considered an even function. So, does this parabola out here have symmetry in the y-axis? No. But any parabola that has its vertex on the y-axis would have symmetry in the y-axis. And that makes it an even function. Okay. So, that's really all there is to that. It's not any more difficult than that. So if I'm looking at, y equals x squared minus 2x minus 3, something of that nature, this will not have symmetry in the y-axis. But if I look at y equals x squared plus 4, it will have symmetry in the y-axis. Or y equals x to the 4th plus x squared will have symmetry in the y-axis. And that's what makes it, as I said, that's what makes it an even function. And you can come down to the rule that if all of the exponents are even, you're going to have an even function. If the exponents are mixed, it could go either way, or it could be neither. Could be even, could be odd, could be neither. Okay? But if all of the exponents are even, which they are not here, so this is not an even function, it's also not an odd function, but they are here, this is even, then we have an even function. I don't even need to look at the graph of that because we know. So then we look at, well, what's an odd function then? For an odd function, xy gets mapped into minus x minus y, which is symmetry in the origin. So if I look at y equals x cubed, y equals x cubed is like that. It is an odd function, okay? Not just because of the odd exponent, but if you can imagine taking this part of my graph, okay, and flipping it over the x-axis and then flipping it over the y-axis, it's going to land on itself. And that means that there is symmetry in the origin. And so therefore it is an odd function, not just odd degreed, it's an odd function. If I have y equals x to the 5th plus x to the 3rd, that will be an odd function because all of the exponents are odd. But if I look at y equals x cubed plus x squared minus 3x plus 7, that's going to be neither because they're even and odds are mixed. So you can always look at it graphically on your graphing calculator too, but basically that's the crux of those problems. And that is all. Thank goodness, right? It's long enough.